right, in the last video we derived formula 5, that if we take the Laplace transform of the Heaviside function, we just get e to the negative as over s. We are, of course, supposing that a is bigger than or equal to 0, because we only care about time values that are bigger than or equal to 0. Okay. What we're going to look at now is formula 14, which is where we're using that Heaviside function as an on switch. But what's interesting here is the function that we're going to turn on isn't just y of t, it's a horizontal translation of y of t. This is y of t shifted a units to the right. So let me just show you an example of how that would work. If I were to look at mu sub pi of t times cosine of t minus pi. Now I know that's a piecewise function. If t is less than pi, we're just getting 0. And if t is bigger than or equal to pi, we'd be getting cosine of t minus pi. So if I graph that, until pi, everything's turned off. We're just at 0. Now, if I didn't have this horizontal translation, if I was just turning on cosine of t at that point, it would almost be like cosine of t had been running in the background. At time pi, it's at -1, and my graph would start down here. That's not what I'm doing. I'm plugging in t minus pi to cosine. So if I plug in pi, I get pi minus pi is 0, cosine of 0 is 1. We're going to be starting at a height of 1. Okay. So rather than thinking of it as cosine was sort of running in the background and then I turned it on, we're like, okay, if I had cosine, it would start at a height of 1. I want to delay everything by pi seconds. But I want to really delay it. I don't want to have it just sort of running in the background and then I'm turning it on. I want, when I turn it on, it's starting where it would have been at 0. So that's what's going on with this shift. Now, could we take a Laplace transform without doing that horizontal transformation? Yes, of course, because it's just defined as an improper integral. I could set up and evaluate that integral. It just turns out that by having that horizontal translation, the formula that we get is a little bit nicer. And we'll see that once we actually get a formula. So let's do that. Okay, so this is going to be defined as the integral from 0 to infinity of mu sub a of t times y of t minus a times e to the negative st dt. And just like when we derived formula 5, I'm going to just break this up into two integrals. The integral from 0 to a of mu sub a of t times y of t minus a times e to the negative st dt, plus the interesting bit, the integral from a to infinity of mu sub a of t times y of t minus a times e to the negative st dt. This is not interesting because this is 0. Because this function is 0 except at a. So if I'm integrating a function that's 0 everywhere except at one isolated point, the integral is 0. So this is the only thing that's contributing anything interesting. Let's just rewrite that piece as a limit. So the limit as b goes to infinity. Integral a to b. Mu sub a of t is now just 1. And so we're integrating just y of t minus a times e to the negative st dt. I'm going to do a u substitution. I'm going to let u equal t minus a. Then du is just dt. And what's perhaps more important is t is u plus a. So I can now rewrite this as the limit as b goes to infinity of the integral. The u value at a will be t minus a, which would be, I'm sorry, I'm plugging in a for t. So that would be a minus a. That would be 0. The u value at b would be b minus a. Still going off to infinity because a is a finite number. Okay. But now I'm getting y of u times e to the negative s times, we said t was equal to u plus a, and then du. Okay. Now, I'm going to just rewrite that exponential limit as b goes to infinity, integral 0 to b minus a, y of u times. This is going to be e to the negative s times u times e to the negative s times a du, because I can distribute the negative s, and then when I'm adding exponents, that corresponds to multiplication. Now, what's lovely about that is there are no u's in that. So this is constant with respect to u. So this is going to be the limit as b goes to infinity of the integral from 0 to b minus a of y of u times e to the negative su du, but with that e to the negative as factored all the way out. I'm going to put that, I can actually factor it outside of the limit because there weren't any b's in it either. Okay, so I'm getting e to the negative as times this limit. But if I take a look at what that limit is, because b minus a is still going to infinity, what I have is e to the negative as times the integral from 0 to infinity of y of u e to the negative su du. That is exactly the Laplace transform of y. Now, we're used to writing this in terms of t. I've changed the name of my variable. I'm calling it u now instead of t. It's just a name. When I integrate with respect to u, there aren't going to be any u's in my answer. Just like when I integrate with respect to t, there aren't going to be any t's in my answer if it's a definite integral. Because what's going to happen with an improper integral like this is I'm going to plug in my limits of integration, except I can't plug in infinity, so I'm going to plug in a variable and then take the limit. I'm not going to have any u's or t's in things. So this is really just a dummy variable. I'm evaluating this at a point and I'm integrating with respect to that variable, multiplying by e to the negative s times that variable. Okay. So what we get is just e to the negative as times the Laplace transform of y. Doesn't matter whether I look at that as a function of t or a function of u. It's a function of this variable that is going just from 0 to infinity, and the Laplace transform changes it to a function of s instead. All right, so it turns out that if I multiply by the Heaviside function and do a horizontal translation of my function, that what I get is just the Laplace transform of that function times e to the negative as. Now, if I hadn't done this horizontal transformation, what would happen here is instead of getting the Laplace transform of y, which is my original function, I'd be getting the Laplace transform of a horizontal translation of y. So it's a lot easier to have the horizontal translation here and just have this be my function. Remember, a way that we can write this, if we like, is e to the negative as times capital Y of s. If I didn't have a transformation here, this would, instead of just being y of s, it would become y of s plus a. So I'd have a horizontal transformation over here. So much nicer to just set it up so that the horizontal transformation is here instead. And that way, this combination of an on switch and a horizontal transformation just corresponds to, when I take the Laplace transform, multiplying by e to the negative a.